Alrighty, so again, these free responses here, all right, are a typical kind of free response, right? A typical kind of free response that we'll see on the AP test, or possibly see on the AP test. For you guys, it's like a little less predictable because since you're going to be taking the VC test, there's more topics that are typical free responses, and so because there's more topics than there are questions, there's more like variety possible, more different possible combinations. For the AB folk, the people that are just taking AB, and then they're just taking the AB test, it's a little more predictable because they have a smaller bank of questions to draw from, and so it's like just less variety is possible. For you guys, this still could be a typical kind of free response that you would see on your test. I believe you guys will have, if I'm correct, I think you're going to have 3 free responses in common with the AB people. Okay, so like you guys can like at the end of the test you could be like, oh, what'd you get for? Did you guys have this one? Yeah, stuff like that. So, but anyway.
How do you know we do that?
Right. Well, I know they tell you not to, but it just can't help yourself sometimes. Just don't let any test graders overhear that. Okay. Anywho, so let's take a look here, number 13. Okay. We've got again CA. This is calculator active here, so that's helpful. I'm going to have our calculators handy. All right, and you can see we've got some regions here, so let's read through this. All right. Please do, again, read through this paragraph here. There's probably important information, or there's often important information given there. All right, so let R be the region in the first quadrant bounded by the graph of G, and let S be the region in the first quadrant between the graphs of F and G as shown in the figure above. Okay, so S is just between F and G and the first quadrant there. Okay, and then R is the region in the first quadrant, also bound just now by G. Okay, the region in the first quadrant bounded by the graph of F and the coordinate axes has an area of 12.142. Okay, so the entire integral here of F. Okay, or the entire integral from 0 to 4 there, that area. So both S plus R, in other words, is 12.142. Okay, the function g is given by g of x equals root x, that's supposed to be an x plus 6 there, root x plus 6 times the cosine of pi x over 8. All right, and the function f is not explicitly given. The graphs of f and g intersect at the point 4, 0, okay, for certain. All right, so letter A says to find the area of S, okay, area of S. So I'm going to try and squeeze this down in here. Hopefully I won't need too much space. It is calculator active, so it's just a matter of setting up, okay? So again, key thing here, right, even though this is calculator active, you need to show your setup, right? We need to show our setup here. So given the information that we have, we can use an integral here to find the area of R, right? And we also know the total area of S plus R. So what kind of expression or could we write here that will allow us to find the area of S? Any ideas? Yeah, Simeon?
12.142 minus the integral of g of x.
Exactly right. Minus the integral, and we'll say from 0 to 4 of g of x dx. Okay? And that's exactly right. Okay, we know the total area of S plus R, right? That's the integral from 0 to 4 below the graph of F there. Okay, so that's S plus R. So we'll just take the total area, subtract the area of R, and that'll leave the area of S. All right, we already kind of saw a problem like this in the quiz, actually, right? So spoiler alert for those of you that haven't taken the quiz yet, but there you go. All right, so this is all the setup that you need. At this point, you can just type the rest of this mess in your calculator and go from there. Okay. A recommendation I might give to you here is that since this function g, we're probably going to be using this several times throughout this problem. I mean, there's a good chance. Okay, so you might want to consider putting this in your y1, and then when you go to do your integrals, you can just do vars, y vars, function y1. Okay, so it's just a tip. Okay, maybe to think about. So I'm going to do that myself actually. So let's see here. Square root of x plus 6 times cosine of pi x over 8. Okay. It would also be a good idea at this point, since we're dealing with trigonometry, to check that we are in the right mode. Okay, I am in radians there, all you physics folks. Make sure you check that you're back in radians. Okay, so Math 9. Bars, y bars, function y1, comma, x, comma 0, comma 4. Okay, and when we do that, I get about 5.204. Okay, but again, if you want to give if you want to give the full decimal there, that's fine. Okay, then you don't have to worry about rounding or truncating. The AP reader will just, cut off after the third decimal place there, and so you can, let them decide whether they want to round or not. But there's your answer. Okay. Questions on A? All right. Letter B. A solid is generated when S is revolved about the horizontal line y equals 5. So I'm going to go ahead and actually draw that up in here. So horizontal line y equals 5. Okay. Write, but do not evaluate an expression involving one or more integrals that gives the volume of the solid there. Okay. So since we are revolving about the line y equals 5, the horizontal line y equals 5, that means we need to integrate with respect to what? X. Okay. So horizontal line y equals 5, respect to x. Okay. And so then our volume here, okay, well, for this, we're going to be using the washer method, right, because we have kind of two radii here. We got this, and we got, there's the little radius, and there's our big radius there. Oh, sorry, I'm on the screen. There it is. Okay, I put that picture in there. Okay. So we're going to do pi integral. Don't forget the pi in front, right? We're rotating here. Pi times integral from what to what? What will our limits of integration be? 0 to 4, right? With respect to x. So we're going to keep that from 0 to 4. Okay. And then we're going to do our big radius. And the big radius is g of x minus 5, right? So curve minus axis squared minus our little radius, which is, yeah, it's that region S there. We don't know. We don't know, okay? So, oh, right, you're sorry, r of x minus 5. Crap. Okay. So, bless you. What can we do here? Yeah, Lily?
Would you use now f of x? Because it doesn't ask you to solve that. And if you can use
That's yes. I don't know why I put an R there. I should have put an F. I don't know why I put an R there. There we go. Okay. Sorry about that. I put little r because that's what little r is, but really we need to be more specific here for f of x there. Okay. And so yes, you can leave it there if you need to. Okay. That's it. G of x minus 5 quantity squared minus f of x minus 5 quantity squared dx. Okay. And there would be the setup. There would be the setup. Okay. For problems like that, the way these are typically graded, just so if you're curious or whatever, problems like this, sometimes they're like 2 points. 1 point could be for like the limits of integration. All right, that's kind of crazy. So you could like totally screw up what goes inside the integrand. As long as you are able to come up with the correct limits of integration, you get a point there. Okay, but then also the integrand would be a point as well, typically. I mean, for a problem like that. Okay, if it was just 1 point, it would be for the entire integral, obviously. But if it's like 2 points, then sometimes they'll break it up and do integrand and integral, integrand and then limits of integration. All right. Okay, letter C. Region R is the base of an art sculpture. At all points in R, at all points in R, at a distance x from the y-axis, the height of the sculpture is given by h of x equals 4 minus x. Find the volume of the art sculpture. Interesting. Okay, so what? We're not rotating here, right? So then what is our what's the other option that we have here? To find the volume of something, the only way we have to integrate and find a volume, right? The only way to use calculus and find a volume is to use that area of a solid with known cross sections. Okay, and that's kind of the situation that we got going on right here. Okay, so the volume, okay, is going to be the integral from a to b of the area of x dx. Okay. And so, since we are, let's see here, at all points at all points in R at a distance x from the y-axis. So, since we are kind of like our function here, okay, the height of these things is going to be 4 minus x. So the height kind of like of our cross section will be determined by 4 minus x. Then the length of it will be distance x from the y-axis there. So this leads me to believe that we're going to be integrating with respect to, well, actually now y, it would seem, right? At all points R at a distance x from the y-axis, the height of the sculpture is given by h of x equals 4 minus x. So it would seem that we want to get that in terms of y, but it's going to be really hard to solve.
I think it is still from the x-axis, because when they say a distance x, they're just referring to your x value. I think. Yeah.
Yes, I think you're right. Yes, because again, we wouldn't be able to solve this to be in terms of y anyway, just with the way that's written. So yes, it's got to be in terms of x there. Okay, so then we'll integrate again from 0 to 4. Okay, and we're going to take our curve, okay, which is going to be determined by, the region R is determined by the curve g of x there. Okay, but times the height. So again, that's now like the side length of our cross section, and then the height of our cross section is going to be times 4 minus x there. Okay, and that will give us then kind of like the area of that cross section, which will kind of accumulate there with respect to x. Okay, and again, now we have the setup, we can just type that into our calculator. So math 9. y1 times 4 minus x, comma, 0, comma 4. Okay, and so I get approximately 17.243. Okay. So we're not explicitly given cross-section shapes here, but we are told that the height of those cross-sections is going to be 4 minus x. So we'll just take our side length, which is just g of x, right, the distance from R to the x-axis like that, and then we'll multiply it by the height of those cross-sections, and then that'll give us then the total volume of our sculpture. All right? So, questions on any of that? So far, so good. Okay. Number 14, also calculator active. All right. So the top line here says, let R be the shaded region bounded by the graph of y equals the natural log of x, and the line y equals x minus 2, as shown above. Okay. And we're asked to find the area of R. So, area, right? We're going to integrate from what to what? Don't know. How can we find out? Set them equal, okay? And since we have our graphing calculators available to us here, let's use those. Okay, let's use those. Okay, let's see here. So for this point, I get 0.1585943 comma negative 1.841406. And then for this point, okay. Remember that when you have multiple points of intersection on your graphing calculator here, okay, when you're asked for what the first curve is, you just make sure your cursor is on one of the curves, and then for the second curve, you make sure it's on the other curve that's intersecting, and then for the guess, this is the key part, you want to move that cursor towards the intersection point you're trying to find. Okay, and then it will know which one to locate. Okay, that's interesting. 3.14. 61932, comma 1.1461932. Okay. And so now, what are our limits of integration? Okay, yeah, 0.15859434. I'd recommend using as much, precision as you can for these. All right, just because of, the intermediate rounding can really throw off our calculations, stuff like that. Same deal then for our upper limit of integration, 3.1461932. Okay, rounding you really want to hold off until the very end to round. I mean, yes, these are even rounded values, but again, to hopefully keep our precision enough so that way we won't be off too bad in our final answer. All right, and then our curves. So we have two curves, right? It's the area of the region between two curves, so we have to do curve minus curve. Which one should we subtract, or which one should we go first here? Okay, natural log of x. And Mario, how did you determine that it had to be the natural log of x?
Just kind of do it.
You looked at it and knew. Okay, fair enough.
Top curve.
It's the top curve, right? That's the idea here. Even though our regions, okay, go from the fourth quadrant to the first quadrant, the principle is still the same. Top curve minus bottom curve. Okay, make sure you put parentheses around that x minus 2 because it's the quantity there. Okay, and now we can just go back to do math 9. Now we have our setup. Okay, and we get approximately 1.949. 0.90927. Okay. So 1.949 there. Okay. But again, your setup is key there. Please make sure you show that setup. Oftentimes there's points associated with that. You don't want to miss out on that by just giving the answer. All right, letter B. Find the volume of the solid when R is rotated about the line y equals -3. Okay, so we're rotating about the line y equals -3. So we're going to be integrating with respect to x. Okay, so it means we get to still keep those limits of integration. 1.5859434. And then 3.1461932. So if y equals -3 is our axis of rotation, that's down here. Okay. What curve determines our big radius there? The top one, which is natural log of x. So it's going to be curve natural log of x minus axis of -3. So minus a -3 squared. Okay, you can make it +3 if you wanted to there, right? Minus, and then our little radius is determined, of course, by the other curve, x minus 2. So x minus 2 minus a -3 squared, and then dx like that. Okay. We can type this into our calculators here. Let's see. Oh, no, that's not going to work well. Nice. Okay, I'll just do it this way then. Pi math 9. And again, really make sure that you are, typing this stuff in to your calculators, right? Get that practice in. Believe it or not, it's something that we need to make sure we're okay with doing, right? It would really stink to be able to set up everything and then not get it right because you can't type it in your calculator too. Okay, you have to be able to use the tool correctly. And this is not a trivial calculation. Okay, here we go. All right, so about 34. 31? 39? Let me see here.
Landers most likely
All right. Well, we'll take consensus then here. So 1986135. Okay.
I do not get that.
That's what I got.
Okay. So here is my yucky mess I typed into my calculator there.
Isn't it supposed to be -3, not +3?
Well, I made it +3 because it's minus a -3. I squeezed in a negative there for that first radius.
Gotcha.
Yes. So it's minus -3 to +3.
Yep.
Yep.
I see.
That's an easy fix on the calculator,
It's
though.
not a
Okay. So, questions on any of that?
It's top curve minus the x's. So it's already minus the negative.
All right, let's take a look here then at this last one. All right. And if you can read it, well, I think we can hear what it says. Let R be the region in the first quadrant bounded by the graph of y equals 2 square root of x, the horizontal line y equals 6, and the y-axis as shown in the figure above. Okay, so there is y equals 2 root 6. There is y equals 6. This is the point 9, 6. Okay, and so for A, we're supposed to find the area of R. So why don't you guys go ahead, since, you know, I read that for you at least. Go ahead, set up for the integral for the area of R. And again, this is a non-calculator one, non-calculator. So you're going to have to do this integral by hand, right? All right. Yeah.
We didn't do C and D in the 14.
Oh my gosh.
Why'd you guys say anything? Just keep going.
I'm sorry. I don't know why. Okay, let's back up then. My apologies.
No.
Let's back up then. Sorry about that. I don't know how I missed that. Okay, wow. Craziness. Thank you for saying something. Sorry, Mario. All right. Letter C. Thanks. Yeah, I know.
Why did you guys say that?
Because they want to know. They want to see what's right and what's not right. So letter C, write but do not evaluate an integral expression that can be used to find the volume of the solid journal when we're about the y-axis.
It does bother me. I don't know.
Okay, sorry about that, guys. Goodness gracious. I was so excited to move on to the one that we can't read that I didn't finish the one that we can. All right, so trying to decipher it. So anyway, now we're rotating about the y-axis, which means we need to integrate with respect to y. Okay. What are our, well, again, so we'll do pi integral. What are our limits of integration going to be? Well, yeah, it's the negative 1.8, blah, 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 up to the 1.14, blah, 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 blah. Okay? So we'll put that in here. So negative 1.841406 and the 1.146192. Sorry, I gotta kind of squeeze it in. There's C. Maybe if I zoom out some, it'll be helpful. There we go. Get it all together on one thing. There we go. Okay. All right, for this axis of rotation, right, we're going to have some space between our solid, well, we're going to have a hollow kind of center for our solid there, so it means we're going to have to use the washer method here. All right, what is our big radius, or what curve determines our big radius here? So again, if you look from the center axis of rotation, which curve is furthest from it? Yeah, so y equals x minus 2. So in other words, it's equal to, yeah, x equals y plus 2 then, right? We're going to have to use that one because that's we want it in terms of y, of course. So y plus 2 minus the curve, right? Sorry, that's the curve minus the axis. The axis here is just what, though? It's just 0. So you do y plus 2 minus 0 if you want, or just a y plus 2 is fine. Again, curve minus axis, right? There. And then minus our little radius, which is determined now by x equals e to the y, okay, the other axis, or the other curve there. So we'll again do e to the y, again minus 0 if you like, or just e to the y by itself there. And then we'll see what that yields here. Pi math 9. Oh, it's just a setup, isn't it?
Yeah.
Jeez, Pete's. All right, sorry about that,
realized
guys.
that
Yeah,
we
sorry
solved
about that.
it, it said right.
Dur. Okay, we could solve that one pretty easily though. We do have our calculators and stuff, but man, oh day. Wake up, Mr. Witt. Here we go. I know, right?
It's the cold. It's the cold.
It's like how I started this class, and now I'm ending the class in the same way. All right. So anyway, letter D. The region R is the base of a solid. Cross section is perpendicular to the x-axis. Okay. Perpendicular to x-axis means that we are going to be doing this with respect to. Yeah, it's respect to x. Okay. All right. Have an area modeled by A of h equals that. Okay. Based on this model, find the volume of the solid. Okay. Cross section perpendicular to x-axis. Have an area modeled by A of h. Where h is the okay. So So for the volume here, all right, we're going to integrate. Again, it's respect to x, so that means we're going to use our x limits of integration. All right, so 0.158594434. Running out of space here. Let's see if I can get this. Oh, did I mess something else up? What am I not being told? 3.1461932. Okay. Well, there would be no pi here. We're not rotating, so we don't need to put a pi in front. Okay. And so then the area formula here that we've got, well, we're told a formula for the area of a cross section, but it does not tell us what h represents here. I'm assuming h represents I want to say it's the distance between the two curves, but that's have an area modeled by A of h equals.
Can we just make our own side?
Or it's just the area. I think this is just. It's just this. Like that. I want to say it's that.
That's it.
Or maybe I should put an X in there instead of an H. Okay. Because it's the area formula, right? We just integrate the area formula. Let me see here if I can. Goodness gracious. I know, right? Call the golf line here. Let me just see. All right, I got two ideas I can do here. Let's see. That's that. Oh, great, but it doesn't have the part D attached to it. Alright, let me take a look at one more thing here. Tells me that I'm not going to have this PDF. We'll see. I do not. All right. Well, I believe that is right, but I'll hold off. I will come back to that one here in a second. I'll check with Mr. Goff in just a minute here. We'll finish up with this last one and I'll come back. I'm pretty sure that's all it's supposed to be, but anyway. All right. Oh boy, good times. All right, so letter A, find the area of R. All right, so now we're moving on to this next one here. All right. All right. Good times. Yeah, this one's not a calculator one, right? All right. All right, we'll just finish through the rest of this here, and then I'll go up and check on that last one. How do you read this? Very carefully. So anyway, so we're supposed to find the area of R. Okay. And so we're going to integrate with respect to x here. Easy enough, right? And so we'll do from 0 to 9. And the top curve 6 minus bottom curve 2 root x dx. Okay? Which is integral from 0 to 9, 6 minus 2x to the 1/2 dx. Okay? Not too bad to integrate that by hand. 6x minus, and then let's see here, 3/2, 4/3, x to the 3/2, 0 to 9. Okay? That lower limit is 0. If we plug that in, it's going to get 0 there, 0 there. So we'll plug in. He's not dumb. I have made mistakes. I have made mistakes. Okay. So 54. Let's see, 9 to the 3/2. Again, this is kind of funky to think about, but again, 9 to the 1/2 power, right, is 3, and then to that third, so that's 27 over 3 though is going to be 9 times 4. It's going to be 36. So 54. Take away 36 there. Okay, so it's going to be 18. Okay. Okay. Maybe we can ask Siri if I got letter D right or not. Said Mr. Goff. All right. Anyway, letter B. Write but do not evaluate an integral expression that gives the volume. So write but do not evaluate, Mr. Whitmire. We don't have to solve it. An integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 7. So again, rotate about the horizontal line y equals 7 means respect to x. Okay, so the volume here is equal to pi times integral from 0 to 9. Okay, and I didn't give myself much space, but that axis of rotation is above our y equals 7. That axis of rotation, y equals 7, is above our curve. All right? And so for the big radius here, since it's y equals 7, which curve is furthest from our center of rotation up here? Yeah, the 2 root x, right? So it'll be 2 root x curve minus the axis of 7 squared minus then 6, the other curve, the inner curve there, minus the axis of 7 squared dx. Okay, and again, I'm just going to set this one up. I'm not going to try and solve it. All right. If you were to solve it here, right, you have to FOIL this one out. Right, 6 minus 7 is negative 1, square root to be 1, so that's not too bad, but you'd have to FOIL that out and then integrate the pieces there. But we're not doing that because we don't have to. Okay. Finally, a volume of solid with known cross sections. That's familiar. All right, region R is the base of a solid. For each y where 0 is less than or equal to y is less than or equal to 6, the cross section of the solid taken perpendicular to the y-axis is a rectangle whose height is 3 times the length of its base in region R. Right, but do not evaluate an integral expression that gives the volume of the solid. Okay, so since our cross sections are perpendicular to the y-axis, that means that they will. We're going to have to write this integral with respect to what? Yes, dy. Okay, so we're going to integrate from 0 to 6, and they do such a good job here of kind of like hinting at it, right? We're only talking about from 0 y to 6. Okay, so y between 0 and 6, stuff like that, and all that. So it, like, you know, it's kind of like more hitting you over the head with the fact that we have to do this with respect to y. Okay, so we're talking about a rectangle here. Okay, and again, our cross section is going to be perpendicular to the y-axis. Okay, so all these kind of rectangles there. Okay, what? Oh, sorry. There you go. Okay, all these we're going to build up a bunch of these rectangles here. Okay, so rectangle area formula. The rectangle area formula is side times height, right? So what is determining the side length of the rectangles here? Let's determine that side length here. From the y-axis to what? To the 2 root x, right? Of course, 2 root x, though, that's in terms of x, so we want to rewrite that. So it's what? 1/2 y equals the square root of x. So x equals 1/4 y squared. Okay, you square both sides. So that's the curve we'll use. Okay, so it's going to be 1/4 y squared. That's going to determine the side of the rectangle, but then the height, whose height is 3 times the length of its base. So then the height will be 3/4 y squared. Okay, 3 times the height of its base. Okay. Right, and then there's our final answer there. Okay. All right, and the next section is arc length. So that ends what we need to cover today. All right, any questions on anything except for 14D, which I'm going to go run up and check with Mr. Goff about real quick. Any questions about the other ones, though? Okay, that's it. So I've got your homework here for you.
The last thing.
Okay. All right, the last things.
For some of you, so glad I'm going to go. I'm being forced to serve this environment. This would actually be the second teacher that I've had to say Latin 1 and Latin 2, Latin 3, Latin 4.
Well, I have 2 teachers.
I'm thrown off because I didn't look at the notes ahead of time. That was my first mistake.
The last day was like a
Just slacking.
All right, I'm going to go upstairs. You're going to Mr. Goff, though.
I know.
You won't have to worry about Mr. Goff. If he has to ask a question of himself, he can just ask himself. I'm going to have to go all the way up there and now ask him. So
It's worth it.
yeah, I'll be right back. All right. So that's your homework, folks. We'll be right back, and then we'll finish clarifying anything if I made a mistake.
Never want to hear Sean's voice again.
We're gonna sit on back.
Yeah, I heard Sean sucks at hockey.
You know what? I'm not as good as I used to be, but I'm okay with
Not
it.
as good as it used to be.
When were you ever good, Sean?
When I was like 5. I did sorry, I woke up and
First.
In here?
Yeah.
oh,
Why? Yeah. I'm actually pretty pumped that I missed my
I can't do first block, but I would totally rearrange the power schedule at this stage.
Yeah. Do you have what period? Fourth?
No, second.
Second?
Second block, yeah. At least I get, it could be worse, I could get like any of the other.
Basically. Yeah, that is a very good point. Oh, solid. Let's get
You played it this way, now you're trying to go this way, so your fingers go.
oh, cool story.
No. Take it off the other.
I'm gonna go get some water. I'm just gonna leave class. You had a good semester with me.
I hate this.
We get to add a whole nother one
I
there.
hate this. I don't care if you send it to one person, just don't.
I just put it on the base and
Mario, throw it.
Distracted. Throw it.
Mario, I know what you're doing. I saw that you leave your hands. Mario, stop throwing dimes.
Pennies. There's a
Dime,
difference.
Lander.
It's a penny.
maybe for you Belgians, I mean, it's a dime.
The other one's a penny.
Simeon, you're a dime.
You're it. Yeah.
I was gonna give it.
Nah, dog, look, you look great on it. Open jail.
What if you make a song and you don't play it?
Yeah, here.
I might
It's such an
She says I know what I'm doing.
Okay, this class ends at 8:30.
Work.
I watched
No, that's not it.
I just watched his
That's not it.
I got ready in less than 10 minutes.
Okay.
I had to play. I felt this
Oh, it won't work now.
Basket is fine.
Tell me what happened.
Not anymore because we have wrestling tournaments on the weekends. So, yeah, your boy's kind of hurting from that. Gotta make a car payment and just got a $75 ticket.
Yeah, no, I didn't know my trip. I felt it.
You get it caught by camera?
Yeah, it wasn't even speeding. It was Sheets and Roy Rogers.
What I miss?
When I'm going to make a right turn to go towards.
All right, so folks, real quick,
Really?
that is correct. Okay. So real quick, again, 14D, that is the correct setup. The idea is here in recent AP tests, Mr. Goff that that when you want to find the volume of a solid with cross sections, sometimes the AP people will just give you the area formula, such as this. Okay, and so in that case, all you have to do is just integrate the area formula there, using, of course, the limits of integration that we get from R. Okay, so nowhere does R really get incorporated into the problem itself, other than just its limits of integration. But we're again, the volume of a solid with known cross sections is the integral of the area of the cross sections, and we're told the exact area of the cross sections right here. So we just use that. All right, so that's now the conclusion.
Yeah, right now. She doesn't have a first walk, but she has a second walk. I don't think she ever gets a first.